Let's look at the classification of text documents using the idea of probabilities. First, let's look at where the probability are in text documents, particularly in the terms. In spoken language, we tend to minimize our effort by reusing old words and expressions. If we use certain terms frequently, we tend to use them even more. And the result of this is words tend toward a minimum in number and size. And the older the word, the more different jobs it can perform. So this is kind of the principle of least effort. And there appears to be a great divide between a small number of words so frequently used and those that are rarely mentioned. And this leads to the Zipf's law. So if we sort words by their frequencies, the word's frequency or a term T's frequency, Ft, is proportional to the inverse of its rank. Okay, so Ft is proportional to the inverse of Kt, which is the rank of term T. Let's look at an example here. So suppose you have a large collection of documents and you count the frequencies of each individual word. And so most likely the word the in the English language may appear to be the most frequently used term. So here, suppose the appears 1,000,000 times, which is ranked number 1. Now proportionally, the number 2 most frequent term, for example B, will be half of that. So B, which is ranked number 2, will become 500,000. And so this is the frequency, which is proportional to half of the rank number 1. And the third term will become 1,000,000 divided by 3, which is around 300,000. And then the fourth rank will be 1/4 and so forth. So this is the inverse relation between the rank and the frequency. Now we can also think of frequency as a probability, right? So in this case, the probability of term T to appear is inversely proportional to Kt, which is the rank. And so let's suppose term the has 0.1 probability to appear. Then the term B is half that probability, which is about 5%. And then the third rank 2 will become 1/3 of that 0.1 probability, right? So this is still, it is the inverse relation between the two. And if you plot this inverse relation on the regular coordinate system, it's going to show this very long tail distribution. And if you transform the coordinates into log-log coordinates with logarithm, it's going to be a straight line. So this is kind of the Zipf law function on log-log coordinates, because Zipf's law is a special function of the more general family of the power law distribution, and which is a straight line here. So these are probabilities, and we are going to use this notion of probabilities, or how likely a term will appear or not to appear, to help us classify text documents. And so we learn about the vectorization of text documents. When we encounter a text document, we can tokenize the document into a vector representation of words or terms. And so let's look at a particular application here, which is email spam filtering, right? This is a very common problem that people deal with today. You want to get rid of the spam emails, but you all want to preserve the regular email that you should receive and you should take a look at, right? So this is a very important problem today, and it's a text classification problem. And so this is an example of a small email collection with 7 documents, or 7 emails, I should say, here. Suppose we only want to look at use the titles or subject of the email for the classification, just to simplify the problem for our discussion here. So in this small collection of training data set, suppose we have already looked at the email and identify which one is a spam, which one is a ham, right? So these are each individual email subjects and their label. Okay, so this one with the title "You have been selected" is a spam. Have a prize for you is another spam. And then another email back here, "Nice to meet you" is actually a ham. It's a normal email that you want to receive. Okay, so how can we train our classifier to learn from this data set and so be able to predict on a new email coming in? Let's first look at a binary representation using the email subjects, right? So in a binary representation for each document, again, we are having the 7 documents here, and suppose we have tokenized the subject and identify these individual terms to represent the documents or emails. For the first email, there are a couple of words in there. "You selected." Okay, so "you selected," these 2 terms appear in the first document. And so "select" and "you" has the value of 1 because they appear. For the other terms, because they do not appear in this subject, their values are 1, and we skip those here, but we should write 0 for the other terms. Okay, and so we can have this binary representation for the emails with the terms. Now, there's a way that we can estimate the different probabilities. So first of all, if we ask how likely, regardless of any evidence, how likely you are going to receive a spam email. And so based on the numbers here, you can count the number of spams versus the number of hams. And so here we have, so the probability of spam, okay, can be estimated by the number of spams here divided by the total number of emails. And so in this case, we have three spams over total 7 emails. So the probability of having or receiving a spam email is 3 over 7 according to this small data set, right? On the other hand, we can also estimate some other conditional probabilities. For example, if we want to see how likely inside the spam emails, okay, so suppose there is an email that we know is a spam. For that email that is a spam, how likely you are going to encounter a term such as price? Okay, so let's say, okay, the likelihood of price, the term given that the email is a spam, how likely you are going to see the term price. And so we basically can count the number of spams here, which is 3 as a denominator, and then count the number of times the price appears in the documents. And so price only appears in 1 email out of 3, so it's 1 out of 3. Okay, we can do the same thing for terms such as meat. right? How likely you're going to see the term meet if it's a spam email, right? And so if it's a spam, and so we can say that out of the 3 spam emails, none of the documents, none of the emails contains the term meet, and so it's going to be 0. Now, there is some problem here because 0 is something we do not want to see. First of all, something doesn't appear here doesn't mean that it will never appear. Okay, so even if it does not appear, if meet does not appear in the spam subset here in your small training set, doesn't mean it's never going to appear. Okay, so there is always some chance that this term will occur. This is the first issue. The second issue is that when you have a 0 probability, in probabilistic modelings, we normally multiply probabilities together. Okay, so when you have a 0 probability in there, regardless of what other values you may estimate, you're going to have a 0 probability in the end. And so this is something we really don't want. And so we have to have some treatment to avoid 0 probabilities. And one treatment is called Laplace Estimator, which is just to add a small constant such as a mu, let's call it mu, to any frequency value that we have. Okay. Now that we add a mu to the numerator, we also need to add another view, perhaps two mu to it, because this is a binary classification problem. Okay, so there are 2 classes. Let's add 2 mu to it. Okay, so in this case, we add mu to the denominator and add mu to the numerator and add 2 mu to the denominator to normalize and to smooth, so to speak, the probabilities. Okay, so we are going to do the same thing for all the other probability values as well. Okay, and so this is kind of one way to smooth the probabilities. This is one to avoid 0 values. Okay, so this is Laplace estimator. Okay, so following this strategy, if we choose mu as 0.05, some of the term probability in the spam class can be computed by, so for example, we have looked at the probability of meet in the spam class, which is originally was 0, but now after this normalization and smoothing, we are going to get a very small value of probability, but it's not 0. Okay, we can also estimate how likely price you are going to encounter price in the spam collection as well. Okay, so we can estimate the conditional probability of each term given spam. We can do likewise in the ham class, right? We can calculate, given a ham email, how likely you are going to see the term meet. Okay, and here you're seeing a bigger probability value for the meet, and then a lower probability value for the price in the ham class, in the regular email collection. Okay, so we can estimate these probabilities. And now, how are these probabilities useful? First, we need to look at a distribution function just to make sure we have the basic formula before we plug these numbers into a bigger one to estimate some probabilities for the classification problem. Okay, so let's first look at this Bernoulli probability mass function, which is actually a very simple function in the binary case. So in the weight Wt, it's a binary representation. So Wt, the weight of a term t, is either 1 or 0, right? Whether it appears or not appear in that document. So when Wt is 1, this is Pt. Okay, so the probability of the term to appear. And when Wt is 0 is the probability 1 minus PT, which is the probability that this term will not occur. Okay, so this is a very simple function to look at both ways, to appear versus not to appear. And so for term price in the spam class, it can be written, the probability of price, W price, can be written as this function, which is essentially meaning when it appears, okay, this is the probability, okay, and this is the probability that for it to not to appear in the spam collection. And so similarly, we can estimate the probability of term weight for U in the Hem class. So this is just to show you another example of how you estimate the probabilities for different terms in different classes. Okay, in here we have the Hem and the spam class, and we have the U, the price, and other terms. And so we need to estimate all the probabilities in these different classes of the terms. Now we suppose we receive a new email, and we have already done the probability estimates for the terms in both classes, and we are ready to do some email classification. Okay, so let's suppose this is the email that we receive, and this email is having a subject line, your price. Okay, now for the sake of discussion, we suppose we are only going to rely on the subject line here. So we don't look into other data. And so this is the only data that we have for the classification. The question here is, which class should we predict? Okay, and so we need to combine those probabilities that we have computed earlier. But how do we put them together? First, we need to look at the representation of this new email. And so this new email marked as D, it has your price. Okay, and according to our representation, it contains the term U, which is a normalized term for your, and then price as well. So we have these two terms and having the one value, and then the other terms, we skip the values here, but we should actually write them as 0. Okay, so basically we're looking at this combination of weights, 0 and 1 weights in this particular email. Okay, and so essentially we need to estimate how likely we're going to encounter this particular combination of 0, 0, 1, 0, 0, 0, 0, 0, 0, 1 values as a vector. Okay, and so the Bernoulli distribution is what we need here to combine the 0 and 1 probabilities. And so let's first look at in the end, how likely, given this particular document representation of the 0 and 1s, how likely this is going to be a Hem, versus how likely, given this particular new email representation, your price, how likely it is a spam. And based on the Bayes theorem, okay, this conditional probability of Hem given D can be computed by P Hem, the probability of encountering a Hem times the probability of D given Hem, or the likelihood for a Hem email to have this exact configuration or exact occurrences of terms for the document in question. Okay. Likewise, we can estimate the conditional probability of spam given this particular email document. Okay, so let's see how we can do that. We already estimated the P Hem and P spam earlier, because just by looking at the number of Hems divided by the total number of emails. We get a probability. But we say that we want to use the Laplace estimator just to smooth the probability. So we add a small number here, small value, which is 0.05 to the numerator and then 0.1 to the denominator to smooth the value. So this becomes the probability 0.57, the probability of a ham. What is the probability of spam? Likewise, 3 spam in the collection of 7 emails, right? So it should be 3 divided by 7, but then we use the Laplace estimator, so we add some small values to the numerator and denominator, and so 0.43 is the probability of a spam. So we have computed p ham and p spam. Now we need to look at the PD given ham versus PD given spam. Okay, so let's look at how we can do that. Assume the term probabilities are independent, and this is a naive assumption. Assume that the terms in the documents appear independently. They have no relation or association with one another, and this is a very naive assumption, but it helps us to do the math. Okay, so if we assume they're independent, what it means here is that an email here, and again, this email can be seen as a combination of these 0 and 1 values, the combination of the 0 and 1 values depending on whether the term appear or not. Okay, so how likely you are going to see the document here with this combination of weights in the same order. Okay, and so according to using the Bernoulli formula, we can quickly realize that this is actually a multiplication, a product of the individual probability values based on the independence assumption. Okay, so the joint probability, so this document can be treated as a combination of all these different terms together. So it's kind of a joint event of the individual terms, and so it becomes the product of the individual probabilities. And this P, the mean does not appear, so we need to estimate how likely the mean does not appear when the weight is equal to 0, given that it is a spam email. Okay, so P weight, PW mean equal to 0 given spam times PW9 is equal to 0 given spam. Okay, and then times price. In this case, price does appear, so it's PW price equal to 1 given spam, and then times the rest of the probability values. So it's the multiplication of all these probability values, and in the end we get something like 0.29. Okay, so this is the probability that a spam email will have this exact configuration, this combination of the terms in the document. Okay, so we can do likewise to compute the probability that a ham email will have this exact email or document configuration of the terms. Okay, and so the result is the product of the individual probabilities given a ham email. And so in this case, we are going to get the conditional probability condition on the ham to be 0.013. Okay, so we have these conditional probabilities, and we can plug the numbers back to the original formula, because originally what we really need to estimate is, given this particular email document, how likely it is a spam versus how likely it is a ham, right? And so what we're going to do is to plug the numbers in. So P spam, regardless of anything else, is 0.43. Okay, how likely you are going to encounter a spam email times PD given spam. The likelihood of a spam email to be in this exact configuration of the document that in question. Okay, so times 0.29, the number we have just got. And so in the end, the result is going to be 0.13 divided by PD. And if we look at the probability for this document to be a ham, we can do the similar computation, and in the end, the result is 0.007 divided by PD, versus this one is 0.13 divided by PD. Now, this PD is the common denominator in the equation, so it doesn't matter. Okay, we only need to compare which one is bigger, and obviously this 0.13 is bigger than the value here, so we are going to predict the email with the subject line, your price, to be more likely to be a spam. So we are going to predict this to be a spam according to this binary representation. Okay, so this is a probabilistic model, and refer to this as a binary model based on the naive Bayes model. Okay, because we only use binary representation for the email documents. But we can also consider term frequencies as well. And so let's look at this same naive Bayes model using term frequencies. Okay, and this is based on a different distribution that we refer to as the multinomial distribution. Okay, so let's suppose now we not only consider the subject line of an email, but also the actual content of an email. And of course, just for the sake of demonstration here, we want to look at small numbers. So suppose, for example, in the second document, when we count the number of times each term appears, we're going to see that, oh, price appears 3 times in the content of this spam email. Okay, and then perhaps the project appears twice in another email, which is a ham. Okay, so we can do all this computation to count the number of occurrences of each term in each email. Okay, and so now that we have considered the term frequencies, the likelihood of an email of a term to appear should be based on the frequency. So, for example, the probability for the price, okay, given a spam, okay, so the likelihood for spam email to contain the price, or I should say, if you randomly draw a term from the spam collection, how likely you are going to encounter the term price. Okay, so this can be estimated by the total number of times the term price appears divided by the sum of frequencies in the spam class. Okay, so we are going to add these numbers up, and it turns out that the result is 15. Okay, so 3 out of a total of 15 is the likelihood that the term price appears in the spam email class. And again, we want to use the Laplace estimator just to avoid zero probabilities and to smooth the probability estimates. Okay, so we can do it for each term in the spam and in the ham class. And so if we do that, and let's suppose we use choose mu equal to 1. Okay, so we are going to add number 1 to each term frequency value. Okay, and of course we add 1 to the numerator, we add 2 to the denominator here. So the P nice, for example, nice appears does not appear at all in the spam collection, so it's 0, but we are going to add 1 to it and divide it by the total. So in the end, this is going to be 1 divided by 15. Okay, and so we can do likewise for the other terms in the spam collection. We can compute the probabilities for each term in the ham collection as well. Okay, so for example, nice, the probability to encounter the term nice in the ham collection is going to be 2 over 19. Okay, so we have these probability values. Now, given a new document or new email to be classified, so now let's suppose we receive an email where the term price appears 3 times, yield appears twice, and nice appears 1 time. So how likely is this email a spam or a ham? So to estimate the probabilities, first we need to look at an entire document as a combination of evidence in the terms. Okay, and if we think of individual term as an event, the document D or the email is the joint event of these individual ones. Okay, and so in this multinomial distribution, we actually only consider the term frequencies. So if they appear, we are going to consider. If they do not appear, the occurrence is actually 0, so we are actually not going to consider here, simply because in the formula you're going to realize that if the term frequency is 0, it's going to you're going to raise whatever number to the order of 0, which becomes 1, and you're going to multiply something by 1, so it doesn't really matter here. Okay, so here we are only going to look at the values, the non-zero values. Okay, and the joint probability becomes the product of individual probabilities, and more specifically, it's a product of each probability T raised to the order of TF. Okay, and then we multiply them together. So in this case, it's going to be the PT P nice to the order of 1, because it appears once, times P price to the order of 3, and then times PU to the order of 2. Okay, so this is the idea based on the product of the individual probabilities. Okay, so if a document belongs to a particular class, the conditional probability can be computed in the same manner. So for a document in a particular class called C, and C can be the spam or the ham, how likely is going to be this exact document representation using the term frequencies? Again, it's going to be a product of the individual term probabilities to the order of TF. Okay, so it follows exactly the same idea here. And so we can put all the probability together by multiplying them in the final estimation. But one thing we do need to consider is that, especially when we consider a large collection of documents with many terms, each individual term probability is going to be very small. And when you multiply small values together, it's going to be extremely small and difficult to deal with using computers. And so the better way to deal with probabilities is actually to take the logarithm of probabilities. And so instead of estimating the likelihood, we are going to look at the log likelihood of having a document in the spam class. So for example, instead of estimating PD given spam directly, we're going to take a look at the logarithm of this p-value. Okay, and so we know that the PD is the product of the individual terms, right? The probabilities of the terms raised to the order of TF. Okay, so the logarithm of the product, if you are familiar with the properties of logarithm, the log of a product becomes the sum of the log. Okay, so this becomes the sum of log PT, okay, raised to the order of TF. And this TF inside the value of the logarithm can be actually, I should put it here, okay, should be brought outside of the logarithm. Okay, so that is what happened here. So TF times log of PT, and then you sum the log likelihood, the log probabilities. Okay, so now that the spam email, the new email to be decided has 3 terms in it: nice, price, and you. Okay, and nice appears 1 time, price appears 3 times, and you appears 2 times. So what we are going to do is going to 1 times the log likelihood for nice, 3 times the log likelihood price, and 2 times the log likelihood of you. Okay, and in the end, we can estimate the log likelihood of a spam email to be in this specific email configuration with the terms nice and 3 times price and 2 times you. Okay, so this is for the spam. Likewise, we can compute the log likelihood of D in the hem class. And so in the end, we'll have this log likelihood estimate. And finally, we can estimate the conditional probability of document D belonging to either spam or hem by using the Bayes theorem. So again, we are going to use the log likelihood value. So the log of probability spam given D, and this is the final probability that we really need to find out. So how likely, so given this particular email configuration or term occurrences, how likely this is a spam versus how likely it is a ham. Okay, and so we can plug the numbers back in. We know the P spam, we know the PD given spam, which is the product of the individual probabilities. Okay, PD is something that we have not computed, but it doesn't matter here. And so in the end, we'll find out that the probability for this document to be a spam is about minus 3.8 minus log PD, versus the likelihood for it to be a ham is about minus 6.6 minus log PD. And so this minus log PD appears in both results, so it doesn't really matter when we compare them, right? We only need to find out which probability is greater. And so this minus 3.8 is actually a greater value than this, and then the value of ham. So again, we are going to predict this email to be a spam. And so this is another model based on the notion of probabilities. But more specifically, this is the general model of naive Bayes with the multinomial distribution. The idea is to consider term frequencies in the model and identify the class that maximizes the log likelihood of the document's membership to that class. And this is kind of the summary of what it, in the end, does to predict. So the notion here is really to maximize the probability value to find out which class has the biggest probability value, and we're going to predict according to that.